Welcome to the series on computer science. As a part of this series, this is a course on Introduction to Artificial Intelligence. This is a continuation of module 3. In this module, module 4, we will be working on the uninformed search. Pretty much we will be dealing with breadth first and depth first search. And in the last module, we saw something on the problem formulation, and we ended up with the question, and the answer to one of the question is given here, where the problem formulation for chess 4 queen problem. Here you would see the initial state where all the 4 queens are not in any place, and the final place where the queens are not defeated or attracted with each other. Okay, it is not attacked by any of the queens. So, queen 3 in the first column, queen 1 in second, queen 4 in third and queen 2 in fourth. In this place it is not attached. So, the state space here can be the configuration of the chess board itself, where you would have a matrix. It can be a 4 cross 4 matrix. This would be 4 cross 4 matrix for the states, and the actions can be placing queen 1 in one of the place. So, that would be the actions. So, following this, we will be moving on into the search introduction. This was given in the last module itself, and here we will be dealing it more detail. Again, I will go through this, where this whenever there is a search, it is going to return a solution when there is a goal is available, or it will return as a failure. First, we will initialize as a frontier. Frontier is something as a, we can have a node where it cannot branch out itself. Pretty much it could be the leaf at that particular point. This is the initial state of the problem, and from the initial state we will be doing again and again. If the frontier is empty, then it is going to be the failure. Otherwise, choose a leaf node from that particular point. It would be something like, suppose we have the nodes like this. The frontier here is going to be frontier for the first node will be 2 and 3. So, at this step it will choose leaf 2 and leaf 3, and it was going to remove 1 from the frontier. So, the remaining would be 2 and 3. This is what it is meaning at this step. Then if the node contains a goal state, then return the corresponding condition. If not, expand the chosen node. If 2 is not a goal, again it has to expand and move on. So, now we will go through that in detail, and this slide again it is taken from the Russell and Norvig, where we would see the difference between what is a node and what is a state. Often people get confused between what is node and state. So, if we take the 8 puzzle that we solved last time, in the last module we solved, we represented, we did not solve, but represented that in the form of a state space. So, in that example we will see what is node and what is state. Having said that, the node is actually the data structure that is being represented, where state is actually the physical configuration. Suppose for, if you take this example, it is, we can take it as a 3 cross 3 matrix. This is the state, whereas when we represent as a node, as a tree, it is a data structure that consists of the state itself, a parent node up to where this node is getting branched, and what is the action that is going to take place from the parent to the child, and what is the path cost. The cost given an intimation in the first last part, where the cost value is 1. So, the cost of moving from one node to the other, that is represented as g of x, along with the depth. What is the depth? Again I would say in the next few slides how to see the depth. And in this case, for example, g of x value is 6. It is just given as 6 right now, just assume it is 6 and nothing to do with how we calculate. It is just an example here. Here in the previous algorithm we saw the expand. The expand function creates new node, which means once we do an action it would go into the next few nodes, filling in various fields, and that is being done by the successor functions or the action. Okay. Now, the infrastructure to search problem, again a continuation of that is, again how do we put it in terms of a variable or the formulation is n, we call it as a node, and n dot state, the state in the state space where the corresponding node correspond. Parent is the parent of that particular node, the action from parent to that node and the path cost. Okay, if we again see, if you just remember the search tree, this is a node and from this node we do an action. You can, this is a parent node, we do an action, this is a child node. This is another node and this is the action, and the path cost typically we right now we are taking as 1. Okay. Now, having done this, how do we search, how do we use it such that to reach the goal? Again, our objective is, given the starting point and given the ending point, how do we reach from the initial state to the goal? And in order to do that, there are 2 ways of doing it. One is by means of the stack or the queue, which you might have learnt in the data structures course. So, the nodes can be used in a queue, and the operations can be either it is empty if it returns no elements, or pop, it returns the first, it removes the first element of the queue and returns it. And how we are going to do it is by means of 3 different operation. Actually, the first one is the queue, and the third one is also the priority queue, which is a slight deviation of the first one. The second one is the last in and first out, which is the stack. And if you remember queue, again you can remember the queue as the queue you are standing in for a queue to get some things. So, that can be 1 by 1. So, this would be 1, 2, 3, I am starting from 1. So, the first one comes in, he goes, then the second one he goes, then the third he goes. This is the operation of the queue, whereas the stack is, assume you are stacking a pile of books on the notebook on table. So, the first notebook is here, the second notebook on the top of it, on the third on the top of it. So, when you think of this queue or stack, have this representation in your mind, so that you will be easily able to understand what happens inside. Now, we will do one example of this stack and queue, but before moving into the search, how do we evaluate the search technique? How do we measure the performance? Performance of a search from the start point to the end point can be done in terms of 4 parameters. One is completeness. We have a search, and does the search always find the solution? Again, we have the search, and if there is a goal, will some technique, can it find, if it is able to find, then the search is complete. That is the first performance measure. Second performance measure is the time complexity. What is the time taken in terms of the nodes in order to reach the initial state to the goal? That is the time complexity, and here we are not going to measure in terms of time in nanoseconds or picoseconds or hours or minutes or years, but in fact it is going to be in the order of n, very similar to that you have learned in algorithms course. And similarly, the space complexity, that would be in terms of the input nodes, how many input nodes can be stored in the memory during the search technique, that is the space complexity. And fourth performance measure is the optimality, and does the search always leads to optimal solution? In some cases it may not lead to optimal solution, which will also we will be doing in this course, particularly in module 5 or 6 we will be doing much about the optimal section. Now, before we go into the details of the breadth first and depth first search, we would see what are the terms typically used in textbooks, and this you might have known earlier in data structures. Nevertheless, this would be a prerequisite for us to understand BFS and DFS. Breadth first search, again I will call it as BFS, and depth first search I will call as DFS. Now, if you assume, if you take for example this tree is a binary tree. Binary is, the branching is going to be 2, B is 2, and the depth D we are going to have at various level. Usually at the root node the depth we call it as 0, at next level depth is 1, at the next level D is 2, which is marked here, and at the down level D is 3. So, this tree is typically a depth of 3, or the maximum depth is going to be m is going to be 1, 2, 3, 3 levels. Now, how do we calculate the total number of nodes? It is going to be, since it is a binary tree, it is going to be 2 power m plus 1 minus 1. M is going to be the maximum depth is for 2, 3. So, it would be 2 power m plus 1 minus 1. Suppose it is, if the branching depth is 3, then it is going to be 3 power m plus 1 minus 1. If it is, suppose if branch say branch number of branches 3, this is how it is being calculated. Now, using these we are going to identify the how the performance is for depth first or breadth first, or in fact any of the searches. Now, before we go into the BFS and DFS in detail, we will see what is informed search and uninformed search. To start with, the categorization of uninformed search, we have different varieties, where the uninformed search is something where you have the search, but there is no additional information of the goal, no additional information, which means we have only the starting point, initial point, and we have only the goal, and we do not know how to reach that goal, and no information about this goal, where is it located, nothing is given. So, those type of search is given under these categories as breadth first, depth first, uniform cost search, depth limited and iterative deepening. And another type of search is the informed search, where with respect to the goal we have some information, some experimental strategy or some information that goal is located in this region. Those kind of information mathematically is given. In those cases, it is called informed search. Examples of it is greedy, A star, hill climbing, simulated, and many more searches are there. And today we will be seeing these two searches, which is depth first and breadth first searches. So, in BFS, this is actually, we call it as BFS. If you take this diagram, this figure, I have drawn 6 nodes, and this is a binary tree with B is equal to branching factor as 2 and the depth as I call here as 1, 2 and 3, but in some books it will call as 2, and depth is 0, 1, 2. The maximum depth m will be 3 m. If I am taking m as 1 here, this is 2 and this is 3. M is the maximum depth, it is 3. The depth is d value is 0, 1 and 2. And we are going to use Q always. BFS, remember it is going to be for is only Q, and DFS it is stack. Q, remember it is going to be of this sort, where we stand in a queue with the line at this point, starting at this point. So, wherever there is another person coming, he would join only at the end, and whoever stands first, he will go out. So, that is the notion behind this queue. And for this BFS, we will have 3 kind of variables. One is the parent variable, where at each point when we visit, we will put that particular parent inside the data structure, and here I have just mentioned as a dictionary kind of thing, which is we normally use in Python. So, this curly brackets is representing a dictionary in Python, where we would specify the node following the parent. And then visited is another variable, just to store which nodes are being visited. And a queue is again a data structure, where in the earlier algorithm we called it as a frontier. That is pretty much the same as a queue, where what are the things that are available. You can remember this as a queue of people standing. The input is typically this tree, and remember, you and I can see this particular tree as such, but to a machine this tree is not visible. We have to feed it in such a way that it has to understand. So, we would put it in terms of some kind of a data structure, where we will say, okay, this is the first node, and following the first node use a linked list to say 2 is entering and then 3 is entering. So, the 3 is linked to 2 and 2 is linked to 1. So, we will use some kind of a linked list to put that in form of a tree, and we would specify which is left and which is right for 1. For 1, 2 is left and 3 is right. Okay. So those information should be given for a machine. So assuming that the information is given for the machine as a tree, this is the tree, input is tree in the form of a linked list. Now the output is going to be goal 5 for this example here. This is the goal and this is the initial state. I am just marking as IS. And the path it has to find is 1, 2 and 5. Okay, so how does it finds BFS through this path is what we are going to do that as an algorithm, actually an example, and then we will go through that algorithm in detail. So at the starting point, visit 1, and once it is visited, it will take that 1 and put it in this visited variable. This visited variable will have 1. Now 1 gets popped and put that here from the queue. So after 1 it gets visited, the leaf nodes after expanding is 2 and 3. Assuming that first the left is coming inside the queue and then the right is coming inside the queue would now have 2 and 3 with 1 out. 1 is moving out, now it has 2 and 3. The parent to 1, see for parent initially for 1 it is none, for 2 it is going to be 1 and for 3 it is going to be 1. So this is step 1. In step 2, after 1 in queue 2 is standing first. So 2 gets visited and once it gets visited it expands into 4 and 5. So this 4 and 5, if the order is going to be first left and then right, it would go here 3, then 4 and 5. That is what is given here, 3, 4 and 5, that is a queue, and the parents of 4 and 5 is 2, which is given right here. So after second step, this is the result. Now in the third step, 3 is visited. Why? Because in the previous queue after 2, the first one is in the queue is 3, so 3 gets visited. So the 3 variables are visited and the queue now has only starting from 4. The parent after 3 it is 6, 3, 6 for 6, 3 is the parent which is being added in the parent variable here. And because 4 is standing first in the queue, visit 4, but after visiting 4 nothing is there. So it would just be as same, this would remain the same. So 4 gets popped out and put it here. Now the person who is standing is 5. At 5 the goal actually is the 5 that we want. So given 5, the visited points are 1, 2, 3, 4 and 5. 5 is visited. Now the queue is 6, but it stops right here. Once the goal is found, it stops. Now and so we got the goal. Now how do we find the action? How do we find the path where how it is going to be 1, 2 and 5? It is by means of this parent dictionary. Now the parent dictionary has all these values. Now from 5 it links to 2, this path, and given this 2 it links to 1. So from 5 2 to 2 1 it links, which gives as 5 2 1. And from 5 to 1, if we just do a reverse of that list, it is going to be 1 2 5, which is this path. So this is how the BFS traverses as a queue from 1, 2 and 5. Now the algorithm for that example, pretty much what we have covered is put it as this algorithm, where you would have the function as BFS with initial state as 1 and the goal test it is going to be 5, and goal test is at each point what happens at each point of the node it will test whether it is a goal, and if it is a goal it would give a success or a failure. Okay, it returns success or failure. Frontier is pretty much the queue that we had as a variable, and explode we will have a expanded node as that is whatever but that is being visited is being given as an explode variable. So, when the frontier is not empty, so we dequeue it, we add whatever the visited state into that visited variable, that is the explode add state. And if it is going to be the goal state, imagine that is at 5, it is a success. Otherwise, put the other rest of it in the queue one after the other until this until we get that goal. If there is no goal, it returns a failure. So, this is an algorithm for BFS. Now, coming into the performance, for any search this performance is very essential. So, if we look at the performance measure, is it complete? Complete is something where if there is a goal and starting from some point, if the search is able to find that goal, then it is complete. For this example, it is complete, and because it is moving in this direction from here, right here and here, from here to here, in BFS normally it is actually complete. If there is a goal, definitely this search technique will find it to be complete. And the time complexity is I have given it is 1 plus b squared. Now, for this example, at this point it is 1, at this point it is b, and in this case it is going to be 2. At this point it is actually b squared, and if we have this has only one node here, suppose we have one more node here, it would be 2 squared, which is going to be 4, and so on. So, suppose if we take for binary tree, it would be 1 plus 2 squared up to n number of d number of d variables, where d is the depth. This depth indicates the point at which there is a goal. Suppose here it is going to be depth is 2. So, it would be at 1 plus 2 squared, that would be the order of 2 squared. The space complexity represents the number of nodes that has to be stored in memory. Here also it is going to be the number of maximum number of nodes that has to be stored is going to be order of b power d, which is 4. This b. And whether is it optimal, again the answer is yes, okay, because at each point there is no other point where this search could have been much better. So, this is going to be optimal. So, this is for BFS. Now, coming to the depth first search, again I have taken the same example, except that the variable alone instead of queue we are going to maintain as a stack. And stack, if you could remember, we can just put it as a box, okay. And we will take the same example here, and exactly the same variable with parent, visited, and stack. The input is tree, the output is goal with a path of 1 to 5, the same considerations that we saw earlier, the same thing is taken. Okay. First visit 1, except here the stack I have assumed first the right node is inserted and after that the left. For example, if you take the first step, visit 1, first we are visiting 1, the stack 2 and 3, first right is stacked, then the left. So, it would be first 3 is stacked and then 2 is stacked, okay. And then the parent of 1 is none, the same considerations as BFS technique, 3 is 1 and 2 is 1. Now, if we look at the stack, after 1 is visiting, the top of it is going to be 2. So, pop out 2, that goes into the visiting variable where 2 is being given here. And after being 2, first right then left. So, 5 is put here and then 3, it should not be 3, but it should be it should be 4, it should be 4. Okay, this is actually wrong. After 2, then it is 5 and this would actually be 4. So, it would be parent of it is going to be 1 none, 3 1, 2 1 and 5 2 and 4 2. So, now if we go to the next one, next step, again if you just continue this, when you put on the top of the stack, you would get such that the parent at last you would end up here. You can compute it yourself and check. You would see that the parent would be 2 1, 5 2 and 4 2, and the path that is being visited 1, 2, then 4, and it will not find it. So, it will backtrack and then 5. It will be the path will be something like this 1, 2, 4 and 5, and actually the path to this graph, it is being mentioned as 1, 2 and 5. So, this is how the DFS is going to proceed. Now, talking about the performance, performance will be 1 plus, and the performance will be complete. It is not complete. Why? Because it can get stuck up in loops. Suppose you have a depth first search going in this direction, all that, and the answer actually lies somewhere here, and in infinite point there will not be any answer at this point. So, it can get stuck in loops, or it may not be able to find. So, it is not complete. DFS will not be complete, whereas time complexity is going to be maximum depth. Wherever there is a maximum depth, that would be the time complexity, which is order of b power m, and space complexity is b multiplied by m. Why? Because it has to store only that path of the nodes where there is only m nodes multiplied by that branching factor. And is it optimal? No. Why? Because there can be some answers in between. So, in this part of the series we have seen DFS searches, and before we close, there is a question: given a binary tree, write a function to find the shortest path from the root node to a given target node using BFS, and a similar function, and you can write a similar function in Python for DFS. Try to give both these functions and try to implement it in your machine in any language possible. We will discuss that function in the next class. As a summary, what we have done today is given an algorithm for search technique and expanded that to different searches, and in the different searches we saw two basic search things. One is BFS, another one is DFS, along with the performance measure. In the next we would see an extension of it with some more example of BFS and DFS. We will see other uninformed search techniques and also an introduction to heuristics. Thank you.